Welcome to this next video in the playlist on ring theory. In this video what we're going to talk about is principal ideal domains, which are another special type of ring. Okay, so principal ideal domains are often abbreviated down to P.I.Ds for short. Okay, and you put dots in between all of the letters like so. So a P.I.D is a principal ideal domain. Okay, so let's start off then with the definition of a principal ideal domain. Okay, so a principal ideal domain then, first and foremostly, it's an integral domain. So the first criterion is that we start off with an integral domain, which I'll just abbreviate down to an ID. Okay, so remember, an integral domain is a non-zero commutative ring, so it's not allowed to be the zero ring, and it needs to be a commutative ring, okay, which also obeys the important integral domain property, which is that if you take two elements in that algebraic structure and multiply them together, and those two elements are not equal to the additive identity, so you take two non-zero elements, two non-additive identity elements in your non-zero commutative ring and multiply them together, you must end up with another element which is non-zero. So the answer will not equal 0 if you multiply two non-zero elements together. The only way that you can multiply two elements of an integral domain together and get 0 is if one or both of the things that you multiplied together were equal to 0. Okay, so that's not true for an arbitrary commutative ring, but if it's going to be considered an integral domain, it is going to be true. So integral domains are those special non-zero commutative rings for which it is true that the only way that you can multiply two elements together and get 0 is if one or both of those elements are equal to 0. Okay, so we start off with an integral domain then, and then on top of all those criteria for an integral domain then, we're going to put another criterion, and that will elevate this integral domain up from just being an integral domain to being a principal ideal domain. Okay, so what's this new criterion that we're going to add on then? Okay, so the new criterion that we're going to add on is that all ideals, and I'll write this down, so if I here is an ideal of our integral domain, and let's denote our integral domain just by R here. So R is going to be our principal ideal domain. So at the moment it's an integral domain, but now the new criterion that it must obey is that if I is an ideal of R, then I must be a principal ideal. Okay, so there must exist, let's say, a little r which is an element of capital R, such that if we generate the principal ideal generated by R, it's equal to I. Okay, so all ideals in a principal ideal domain must be principal ideals. There must exist some element of the principal ideal domain which, if you construct its principal ideal, will give you that ideal. There are no ideals that are not of this form. That is what a principal ideal domain is. And I should stress that not all integral domains are principal ideal domains. Okay, there are examples of integral domains where some ideals simply cannot, are not equal to any of the principal ideals generated by all of the elements in that integral domain. So a principal ideal domain is a special type of integral domain in which it's true that the ideals are very simple, they're all principal ideals. Okay, so let's see some examples then of principal ideal domains. Okay, so the first really trivial example then of a principal ideal domain is all fields. Okay, and that's not exactly one example, it's a whole category of algebraic structures that are all principal ideal domains. Okay, so remember, a field is a non-zero commutative ring in which all non-zero elements have a multiplicative inverse. Okay, and we know that all fields have a very simple ideal structure. The only ideals in a field are the zero ideal and the unit ideal. And both the zero ideal and the unit ideal are principal ideals. The zero ideal is the principal ideal generated by 0, and the unit ideal is the principal ideal generated by 1. Okay, so trivially, all fields are principal ideal domains because the only two ideals that they have are principal ideals. Okay. Oh, and I should stress also, all fields are integral domains. As soon as you insist on all non-zero elements having multiplicative inverses, then you can prove very simply that you can't multiply two non-zero elements together and get 0 in a field. Okay, so all fields are integral domains, and it is the case that all ideals are principal in a field. Okay, so they satisfy the criteria for a principal ideal domain. The next thing to say is that actually all Euclidean domains, which we have talked about in a previous video in this playlist on ring theory, all Euclidean domains are actually principal ideal domains. So in the video on Euclidean domains, we prove that in a Euclidean domain, all ideals are principal, and since in the definition of a Euclidean domain we insist that they are integral domains, then they do indeed obey these two properties. So I'll just remind you of what a Euclidean domain is. So a Euclidean domain is a non-zero commutative ring that is an integral domain, okay, which has a Euclidean size function on it. So you can put a function onto it which will ascribe to all the elements of the Euclidean domain except the additive identity element a non-negative integer, and that Euclidean size function has to give rise to a Euclidean division algorithm where if you have A and B, which are arbitrary elements of your Euclidean domain, so I'll just write this down. So remember, if you have A and B, which are elements of your Euclidean domain, which I'll just denote R here, and B is not equal to the additive identity, so you can't let B equal the additive identity here, then you can always write A as some multiple of B plus a remainder term. So Q and R are just elements of your Euclidean domain, okay? And either A is going to be a perfect multiple of B, in which case the remainder will equal 0, so the two possibilities are R is equal to 0, or at the very worst, if there is no multiple of B that is actually equal to A, then you do have to have a remainder term here. It is possible to find a multiple of B such that the remainder that you have to add on to get A will have Euclidean size less than, strictly less than the Euclidean size of B, so where F is denoting our Euclidean size function here, and that's called the Euclidean division algorithm. Okay, so a Euclidean domain is an integral domain then that has a Euclidean size function on it which gives rise to the Euclidean division algorithm. And we proved in the video on Euclidean domains that if you have a Euclidean domain, all ideals in that are principal. It follows from having this Euclidean division algorithm that all ideals are principal, and therefore all Euclidean domains must be principal ideal domains because they were all integral domains, and now we know that all the ideals in them are principal ideals, and therefore they do satisfy the two criteria of a principal ideal domain. Okay, so what examples of Euclidean domains do we have? Well, all fields are Euclidean domains, but we've already stated that one, so that's not a new example. But other examples of Euclidean domains are the ring of integers. Okay, so that's not a field, but it is a Euclidean domain, and therefore it's going to be a principal ideal domain. And in fact, we've already seen in previous videos in this playlist on ring theory that all the ideals in the ring of integers are principal, okay, many times. And another example of a Euclidean domain then are the rings of polynomials where the coefficients are over some field. Okay, so these can have a Euclidean size function put onto them where all polynomials, except of course the zero polynomial, are just mapped onto their degree, and that gives rise to a Euclidean division algorithm on that ring of polynomials. Okay, so there's another example of a Euclidean domain, and therefore it's also a principal ideal domain. Okay, so again in here, this is an integral domain where all of the ideals are principal, and therefore this also satisfies the criterion for a principal ideal domain. Okay, so the question now arises, if we know that all Euclidean domains are principal ideal domains, is it also the case that all principal ideal domains are Euclidean domains? I'm going to state this result without proof, but it is not the case. Okay, so drawing a picture basically, if this blob here, if this set here represents the set of all principal ideal domains, okay, so this is the set of all principal ideal domains, then a sub-portion of that is the Euclidean domains. So I'll just represent these by EDs here. Okay, so all the Euclidean domains are principal ideal domains, but there are principal ideal domains that are not Euclidean domains. Okay, so I'll state that without proof. Okay, but don't go thinking that all principal ideal domains are Euclidean domains. It's simply not true. There are principal ideal domains that are not Euclidean domains. Okay, and that picture easily shows you that. Okay, right. So what do I want to show about principal ideal domains now? Well, the first result that I want to give you about principal ideal domains is relating to prime ideals in principal ideal domains. I want to show that if we have a prime ideal that is not the zero prime ideal, then it's actually a maximal ideal. Okay, so let me just remind you of what a prime ideal is. Okay, so this definition goes for any commutative ring, so we can certainly apply it for a principal ideal domain here. Okay, so remember, a prime ideal, which we'll call capital P, of a commutative ring capital R, okay, is a special ideal because it has the property that if you take any two elements from outside of the prime ideal, so let me write this down, so for all A and B that you can possibly pick from outside the prime ideal, okay, so they're from R subtract P, okay, so drawing a picture here, if this is our entire commutative ring here, capital R, and here is our prime ideal, capital P here, I am now saying you pick me some A and B from the portion of the ring that is outside of the prime ideal. Okay, so this is our ring capital R here in green, and then we've got our prime ideal here, which I'll outline in orange here. Okay, so I'm saying pick some elements that are outside the prime ideal. So A and B are both outside the prime ideal. Okay, if you then multiply these two together, so A times B, of course just using the operation that's in our commutative ring here, that will also be outside. Okay, so I'll just put then A times B is also outside of the prime ideal. Okay, you cannot multiply two elements that are outside of the prime ideal and get something that is then inside the prime ideal. The only way to multiply two elements together and get something that's in the prime ideal is if one or both of them are already in the prime ideal. So if you do multiply two elements together and get something within the prime ideal, then you can conclude that either one or both of them are elements of the prime ideal already. Okay, so that's the definition of a prime ideal, an ideal for which it is true that the only way to multiply two elements together and get something in that ideal is if one or both of them are elements of the prime ideal. Okay, so that's a definition that works in an arbitrary commutative ring. What I now want to show you is that if we are working in a principal ideal domain, then all non-zero prime ideals are actually maximal. Okay, so in a PID, so now we're going to elevate our commutative ring up here from just being a commutative ring to being a principal ideal domain, and it's non-zero prime ideals. Okay, and this is important because one of the prime ideals that will always be a prime ideal in an integral domain is the zero ideal. Now in an arbitrary commutative ring you can't say whether the zero ideal is going to be a prime ideal or not, but if you're working in an integral domain then you can conclude that the zero ideal is a prime ideal. Now of course we're working in the principal ideal domain, but principal ideal domain is an integral domain. Okay, so you can therefore conclude that the zero ideal is a prime ideal. Okay, and the reason of course for that is that it will obey this criterion. So if we substitute in for P here the zero ideal, then if the only way that we can get two elements to multiply together to give us an element of the zero ideal, and of course the only element of the zero ideal is 0, so the only way we can get two elements to multiply together to give 0 in an integral domain is if one or both of them is equal to 0, and therefore we can conclude that the zero ideal obeys the criterion for being a prime ideal if we're working in an integral domain. Of course that isn't true if we're not working in an integral domain, if we're just working in an arbitrary commutative ring. Okay, so in a principal ideal domain, all non-zero prime ideals, so I want you to get a prime ideal that is not the zero ideal. Okay, I know the zero ideal is the prime ideal in my principal ideal domain because it's an integral domain, okay, but I don't want to count that one in this theorem. Okay, so all non-zero prime ideals are maximal. Okay, so they're maximal ideals. Now, of course, that isn't going to be true for the zero ideal. The zero ideal is not going to be a maximal ideal, because remember, a maximal ideal is one that is maximal with respect to proper ideals, and I'll just explore that a little bit more now. So I'll remind you of the definition of a maximal ideal like I did for the definition of a prime ideal, and then we'll prove that this is true. So, what's meant by a maximal ideal? So, a maximal ideal is usually denoted capital M here, okay, and it will be, again, a definition that you can use in an arbitrary commutative ring. So, you don't need your ring to have any higher structure than just being a commutative ring to define what is meant by a maximal ideal. So, a maximal ideal, capital M here, is an ideal that is firstly a proper ideal. Okay, so M must be properly contained within R. Okay, so it can't be the unit ideal is the first thing. And it has to be maximal with respect to proper ideals. And what that means is that there cannot exist an ideal that is properly in between these two. Okay, so there cannot exist an ideal I which is properly in between the two, by which I mean which properly contains M. So this is a proper containment here. So there can't exist an ideal that properly contains M and is itself properly contained in R. Okay, so if you want to make an ideal that contains M, either you have to just use the ideal M, or you have to go up to the entire unit ideal, the entire ring. You can't find a bigger proper ideal than M, okay, that fully contains M. That's what it means to be a maximal ideal. You are maximal with respect to proper ideals. There is no proper ideal that is bigger than you and properly contains you. Okay, the only ideal that contains you properly is the entire ring, which is, of course, is not a proper ideal. Okay, right, so that's what it means to be a maximal ideal. What we now want to show is that all non-zero prime ideals, so this isn't the zero ideal, all non-zero prime ideals are maximal. Okay, so we want to show that this is true in a principal ideal domain. It's obviously not true in an arbitrary commutative ring, but in a principal ideal domain it is going to be true. Okay, so how are we going to show this? So we're going to take an arbitrary prime ideal, okay, and we want to show that it's a maximal ideal. Okay, so let's start this. So let's say we'll call our principal ideal just R again. So let P be a prime ideal of our principal ideal domain R. Okay, now of course what we can say, because our ring here, our commutative ring here, is a principal ideal domain, we can conclude that this prime ideal has to be a principal ideal, because all ideals are principal in the principal ideal domain. Okay, so let's say that it's a principal ideal generated by P. So let's say the principal ideal generated by P, where P is just some element of the principal ideal domain capital R, is equal to our entire ideal capital P. Okay, so excellent. Now what we want to show is that there cannot exist another ideal that is properly in between the two. Okay, so let's assume that we have some other ideal that is in between the two. I won't say it's properly in between the two. Okay, it's in between the two. So let's say that we've got some other ideal, and of course this other ideal will be a principal ideal because we're working in the principal ideal domain. So let's say it's the principal ideal generated by this element M here, and let's say it's between the principal ideal generated by P and the entire principal ideal domain, capital R. So note, I haven't said it's properly in between. I've put the lines underneath these. So it's not necessary, it doesn't necessarily properly contain P, and it's not necessarily properly contained in R. It's an ideal that's in between the two. What I aim to now show is that this principal ideal generated by M that's in between these two is either equal to P. So I want to show that either it's equal to this one, or it's equal to this one. And then if I can show that, then obviously it's true that there's nothing that's properly in between the two. So I'm going to say, okay, we're going to try and find an ideal that is in between the two of these. So it contains this prime ideal here, which is the principal ideal generated by P, and it's contained within the entire principal ideal domain. But what we want to now do is prove that there's only two options. It can either be just the principal ideal generated by P, or it can be the entire unit ideal here. Okay, it can't be properly in between the two. Okay, and remember, the reason I've said that this is the principal ideal generated by this element M is simply because all ideals are principal. So if we've got an ideal that's in between the two of them, it will be generated by something. Okay, right, so let's get on with this then. So, if the principal ideal generated by M contains the principal ideal generated by P, then that means that P is going to be within the principal ideal generated by M. That's perfectly reasonable. Okay, so the first thing I can conclude from this is that P is an element of the principal ideal generated by M. Okay, because if the entire principal ideal generated by P is contained within this, then one of the elements that's in here is certainly P, so P is going to be in here. Perfectly reasonable. Okay, now, anything that's in the principal ideal generated by M is of the form some element of the ring times N. Okay, so that means that P is going to be equal to a multiple of M. Again, that's just using the definition of a principal ideal. Okay, so R here is just some element of our principal ideal domain, capital R here. Okay, right, so that's perfectly reasonable as well. Now what we're going to do is use the fact that this is a prime ideal, okay, because look, I've got two elements here that are being multiplied together and giving me P. This is a prime ideal, okay, by assumption we started off with it as a prime ideal here, okay, so that means that the only way that you can multiply two elements together to give this element of our prime ideal is if one or both of them are actually elements of this prime ideal. Okay, so let's take the two options. So one of the options is that M could be an element of the prime ideal. So M could be in the principal ideal generated by P, which is our prime ideal. But the instant M is in the principal ideal generated by P, what does that tell us? Okay, well, because this is an ideal, it has to be closed under multiplication. So all multiples of M by any element of the ring have to be in there. Okay, so this now tells us that the principal ideal generated by M would be contained within the principal ideal generated by P. But if you take this statement here and take this statement here, you can then conclude that the principal ideal generated by P would equal the principal ideal generated by M. So if M is in the principal ideal generated by P, then you can conclude that actually the principal ideal generated by M was the same as the principal ideal generated by P, i.e. you can conclude this arrow here. Okay, so this is all going rather well. So we've shown that if M is in the principal ideal generated by P, if M is the one that's in the prime ideal, then that forces this principal ideal generated by M to be the principal ideal generated by P, to be the prime ideal, basically. Okay, so now let's take the only other option. So let's assume that this wasn't true then. So M was not in the principal ideal generated by P, so now we'll assume M is not an element of our prime ideal here. But that now forces R to be in the principal ideal generated by P. So R is now in the principal ideal generated by P. Okay, there's no other way because this is a prime ideal. So one of them has to be a multiple of P, basically. It has to be in the prime ideal. Okay, so now what can we conclude from this? So if R is in the principal ideal generated by P, what does that show us? That shows us that some multiple of P is equal to R. So I can write R as, let's say, P times S, and I'll do it the other way around from the way I did it here. You'll see why in a moment. Of course, we're working in the commutative ring, so it really doesn't matter which way round I put the S and the P. Okay, so I'll put them this way round. So I can multiply P with some element of the ring to give me R here. So again, S here is just some element of my principal ideal domain. Okay, and it must be the case that you can do that, otherwise R wouldn't be in the principal ideal generated by P, and therefore it wouldn't be in the prime ideal, but it has to be in the prime ideal if we're assuming that M is not in the prime ideal. Okay, and if M is in the prime ideal, we've already shown that from that we can conclude that this ideal generated by M is equal to the prime ideal. Okay, so we're now going to this second line here. Now, what can we conclude from this then? That if R is equal to P times S, we'll just substitute it in here. What we can now do is write that P is equal to P times S times M here. Okay? There's nothing wrong with that. If R is equal to P times S, I can substitute it in there. That's absolutely fine. Of course, I'm assuming now we're used to the fact that multiplication is associative in the ring, so I haven't bothered to put brackets in there. Okay, now we use the cancellation law that holds in integral domains. In integral domains, you can cancel that p, provided that you know that p is not equal to 0. And of course we know that p is not equal to 0 because we assumed that our prime ideal was not the 0 ideal. And if our prime ideal, if p here was equal to 0, then our prime ideal would have been the 0 ideal. Okay, so because p is not equal to 0, we can cancel it off, basically, both sides, and that's because we're working in an integral domain, which of course the principal ideal domain is, and therefore what we end up with is that 1 is equal to s times m. Now, why is that a problem? Or rather, why does that prove exactly what I wanted to prove? Well, s times m, s is just some element of the ring, the principal ideal domain here. So s times m is going to be in the principal ideal generated by m. So what we can therefore conclude is that 1 is in the principal ideal generated by m. And the instant you have 1 in an ideal, then you have to have all elements of the ideal, all elements of the larger ring in that ideal, because you have to have all multiples of 1. And what are all the multiples of 1? They're the entire unit ideal. So this now shows us that the principal ideal generated by m is equal to the entire ring. So either you can take this way round, in which case you conclude that the principal ideal generated by m is the same as the principal ideal generated by p, or you can take this way round and then you conclude that the principal ideal generated by m is the entire ring. So I have now proven that if you have an ideal in a principal ideal domain that is in between a prime ideal and the entire ring, then it cannot be properly in between the two. It has to either be equal to the prime ideal or it has to be equal to the entire unit ideal. Okay, and that therefore proves that any prime ideal in a principal ideal domain is maximal. There is no ideal that is a proper ideal that is properly containing your prime ideal. Okay, it's maximal with respect to proper ideals. So all and I should make sure that's clear, all non-zero prime ideals, I think before I said all prime ideals, all non-zero prime ideals in a principal ideal domain are maximal ideals. The one exception is the 0 ideal, which is a prime ideal, but which obviously is not a maximal ideal. Any other ideal that's a proper ideal will contain that, and therefore it won't be a maximal ideal, unless of course you're working in a field. We can, however, conclude that all non-zero prime ideals are maximal ideals. Okay, so we'll have a break here, and in the next video what we'll do is explore one final theorem which is interesting with regards to principal ideal domains.